All right, the conditions required for an object to perform simple harmonic motion. Remember, a spring is going to cause a simple harmonic motion like this, right? Remember that this spring exerts a force that's equal to minus kx, right? The minus means that if you displace this to the right, the force is to the left, and that it's proportional to the distance from the equilibrium, okay? Put that into words, okay? And then calculate the mass of the block. So we have a 0.52 kilogram mass performs simple harmonic motion with this period, right? Then they put a wooden block whose mass we want to figure out, right? And it oscillates more quickly, right? So therefore it's got less mass. And the formula I'm going to use for this is that the period is, and this is in section 9.1, 2 pi square root of m over k, right? Now, how do we do this? Well, we're going to set up two equations, and we have two variables, right? We can solve for one of them, right? So let me just show you this. I'm going to go 0.86 equals 2 pi square root of 0.52 over k. Now, by the way, it might be smart to calculate k. What is k? Can't you calculate k from that, right? Okay. And then in the second instance, 0.74 equals 2 pi square root of some other mass divided by k. Now, you don't know k and you don't know the mass, this mass, right? But you can divide this side by this side, right? And you'll end up with the 2 pi's go the way of the bison, right? You get 0.86 over 0.74 is equal to the square root of 0.52 over the square root of m. And you can solve that using algebra, okay? There it is, right? In carrying out the experiment, okay, so then that'll give you a mass, right? So you'll figure out the mass, right? And then the student displaced the block horizontally. So now we've got the mass of this block. And I'll give you a clue. The mass of the block is between 0.35 and 0.4 kilograms, okay? And you'll get that mass, right? And then it says determine the total energy. Well, you can do it this way, right? You can do it this way. You could go total energy is 1/2 the mass, right? This is our mass that you figured out, right? It's that number that's between 0.35 and 4, right? And then omega squared, which is going to be 2 pi over, what's our period? 0.74, right? Right? And then x naught squared is going to be 0.048 squared. It's not a lot of energy. It's between 0.01 and 0.05 joules, okay? Not a ton of energy, but you can figure it out that way. But here's the other thing you can do is, can't you find the spring constant of this thing, right? The spring constant just begs us to find that, right? So 0.86 is 2 pi, whoops, square root of 0.52 over k, right? And you can solve that for k. K ends up being about 27.7566 approximately newtons per meter, right? So solve that for k, and then isn't your total energy just 1/2 kx naught squared? Right, just plug that in, right? Plug the 0.048 in for that, and you're set. Okay. Is this easier or is that easier? I just don't know. They're the same. All right, let's keep going. Okay, a second spring is placed in parallel when the experiment is repeated. Well, if you put a second spring in parallel with this thing, okay, it's going to oscillate faster. You basically double the spring constant, right? And so if you shorten the period, but you have the same, let's think about this, right? Okay, if you shorten the period, but you have the same uncertainty of period, right? So the first thing you want to do is talk about what it does to the period, right? I think, right? Then if you shorten the period and you have the same uncertainty of time, doesn't the fractional uncertainty of time over the time, if that's smaller, doesn't that make this whole fraction bigger, right? And so then you can surmise that if that fraction is bigger, that's going to change the fractional uncertainty of the mass of the block in some way. Now, I was very specific about this, right? But but you don't have to be that specific. It's 3 marks, and just make that general argument. So what happens to the period? When the period decreases, what happens to the fractional uncertainty of this, right? If this stays constant and this gets smaller, right, what happens to that fractional uncertainty? If that fractional uncertainty changes, what happens to the fractional uncertainty of the mass of the block? Okay. Okay. And then here, this is a spring, right? We've got this spring like this, right? And there's a wave traveling down this, a longitudinal wave traveling down the spring. Okay. Other than that, it's totally unrelated to the previous part of this problem, right? A point on the graph has been labeled that represents point P on the spring, right? Okay. State the direction of motion of P on the spring. Well, what you got to understand is that P sits still, and then this wave is moving over it. Okay. And so it was displaced to the right, and it's now about to be displaced to the left. Okay? It was all the way to the right, and now it's on its way pretty soon. In the next second, this will be over P, right? This thing will be, right now this is on P. This was on top of P, right? And now it's going to be here, right? So it's at 0, and then in another instant, it's going to be displaced to the left. So talk about the motion of that, right? Okay, and then explain whether P is at the center of a compression or the center of a rarefaction. A rarefaction is where the springs are spread apart. Okay, now keep in mind that the springs in front of P are displaced to the right. Okay, right. The ones behind it are displaced to the left. Okay, so talk about that. Is it compressed or is it rarefied? Is it stretched? Okay. Remember, so the ones in front of it have been stretched to the right. The ones behind it have been stretched to the left. Okay, think about that.